Okay, this is just a brief overview of Le Chatelier's principle with the primary goal of helping students interpret Le Chatelier's principle, concentration versus time graphs. Um, Students do have to be able to define Le Chatelier's principle, and the textbook definition is when a system at equilibrium is disturbed, the equilibrium shifts in the direction that opposes the change until a new equilibrium is reached. So basically, whatever you do to the system, it has to do something to return itself to a new equilibrium. For the diploma, there are of course 4 changes or stresses students have to be able to understand for Le Chatelier's principle: concentration, temperature, volume or pressure, and the addition of a catalyst. So the first change I'll go over is a change in concentration. So in this example here, the concentration of a reactant is increased. So now you have more reactant on the reactant side. The system has to return to equilibrium by getting rid of it. Luckily, there's only 2 possible answers. It can either go forward or reverse, and since you've now added something on the reactant side, in order to use it up, it must shift to the forward direction in order to return to equilibrium. So if you remove a product or increase a product, the system has to return to equilibrium, but now you have too much on the product side. The system must shift in such a way to use up what's on the product side. Well, the only thing it can do is go forward or reverse. Well, since you've added more to the product side, it has to go in the reverse direction. And there will be a question somewhere on the diploma asking what effect a concentration change or what effect a stress on the system will have on the equilibrium constant. It will only have an effect on temperature, as we'll see in a few minutes. So in terms of interpreting a graph, for example, in this first one, this is straight out of the textbook, you're increasing the amount of HF, so the system now has to go forward in order to use up what was added. And if you look at the lines very closely, you can see the reactant is slightly decreasing while the products are increasing. So in terms of quickly reading one of these graphs, if a student sees one sharp change in the data and the rest of the lines are gradual, that's a giveaway that it's a concentration change. Changes in temperature. Well, the easiest way to interpret temperature is to remember in thermochemistry that you can put energy terms directly into the balanced equation. The first example we'll look at is endothermic, so energy has to be on the reactant side of the equation. So if we were to decrease the energy, or decrease the temperature, we decrease the energy, it's like we have less reactants to work with. So students can just interpret this like they would concentration. You're missing or you're reducing something on the reactant side, therefore the equilibrium has to shift in the reverse direction in order to replace what was taken out and return the system to equilibrium. Conversely, if you're adding energy to an endothermic system, you're now adding energy or reactant to the reactant side, and the system has to shift in the forward direction to take out what you've put in and return the system to equilibrium. In exothermic reactions, the energy is now a product, and again, treat it like a concentration or an amount of product. So if the temperature is decreasing, you're now taking energy out of the system, so a product's decreasing. The system has to shift in the forward direction to replace what you've removed and bring the system back to equilibrium. If you're adding energy, it's like you're adding a product or adding more concentration on the product side, and the system has to reverse to overcome the change inflicted upon it. Now, one of the questions they do ask on the diploma is how it will affect the equilibrium constant. And basically, if you affect a change on the equilibrium and it goes more in the forward direction, the K will increase, and if it affects a change that the reaction will favor the reverse direction, it'll affect a K decrease. In terms of interpreting graphs, the temperature change is easily identified because all changes in the data are gradual. So if we look at this one, this is the temperature decrease. So we're taking energy out. The system is going to shift in the forward direction to replace what is taken out of the system and return to equilibrium. So since we're favoring the forward direction, we should see an increase in the product. And if you look at the graph, you see the products increasing and the two reactants slightly decreasing before they return to equilibrium. Pressure. Pressure is the most difficult of the concepts to apply to one of these graphs and to apply Le Chatelier's principle in general. Students may have to remember their Boyle's law from chemistry 20 in that if the volume is decreased, the pressure would increase, because if you remember, it's an inversely proportional relationship between P and V. In any case, when you increase pressure, what most students know is that the system will shift into the direction of fewest moles. And if you decrease the pressure, the system will shift into the direction of most moles. And what I tell my students is they can either memorize this or they can try and understand it. And the way I try and get them to think of pressure is how it's defined when they learned it in chemistry 20, and that is as collisions with the sides of a container. So if you have more collisions, you're increasing or experiencing high pressure. If you have fewer collisions, you're decreasing pressure or experiencing low pressure. So when you look at your equations, the previous examples, if we increase the pressure of the system, we now have a pressure imbalance. So what Le Chatelier's principle is, it's going to do the opposite to overcome that stress. So if we're looking at pressure, if we're increasing pressure, it has to go in the direction you would have fewer collisions. So where are you going to have fewer collisions? Where you have fewer moles. So to bring the pressure down, it's going to have to favor the forward direction, because on this side, there's 5 moles, and on this side, there's 4 moles of particles. Conversely, if we decrease the pressure, the system is going to want to do the opposite to bring the pressure back up or return the system to equilibrium. So in order to bring the pressure back up, it has to go in the direction of most collisions. In this case, you have 5 moles on the reactant side and only 4 moles on the product side. So the direction favored is the one with the most particles, more collisions, higher pressure. And if you go back here, a good strategy is that if you quickly look at the equations on the diploma, if there are the same number of moles on each side of the equation, pressure will have no effect, because you're basically going to have the same amount of collisions on both sides. So varying the pressure will not shift the direction in either, or the equilibrium in either direction. When you're looking at the concentration versus time graphs, what you're looking for is that all the changes are sharp. There are no gradual changes in a pressure change. And you can think of it as you're changing the volume, so you're changing the concentration of every single species, so they're all going to look like sharp changes. The effect of an addition of a catalyst is that while a catalyst will cause the reaction to speed up, it will only cause the equilibrium for you to attain equilibrium faster. So in terms of looking at a graph, it will have no effect. And what you'll see is if a question is asking you about equilibrium, with a catalyst, the lines will remain horizontal. It'll appear that nothing is happening. And students need to know this, and there's just a brief summary right out of the textbook of the stresses and their effect on equilibrium. Now, unfortunately, in Nelson Chemistry on page 699, there's only one question with this graph. So there's only really one chance for students to practice this from the textbook. And it's a good idea to go through this question in great detail with the students to make sure they can understand it. However, you will see this type of question on the diploma. So there's a couple of strategies you can teach students to quickly employ in order to make this question a little easier. The first thing I do is I look at the picture and I immediately look at the shape. The first thing I would do is check everything's gaseous here, so pressure will have an effect. And then I check the number of moles on each side of the equation. And right away I know pressure is going to have an effect on this. But I also know pressure is probably the most difficult to leave or to work with, so I'm going to leave that for last. Next thing I would do is I'd look at the shape of the curves. Well, right away you see that X has got to be some sort of catalyst or some sort of thing that's not concentration, time, or temperature or pressure. So that one's an easy to identify. If you look at the first line here, there is one sharp concentration change. Everything else is gradual, so you must be changing a concentration of the products or the reactants. If you look at Y, all four changes are sharp. That has to be your pressure. And if you look at Z, all four changes are gradual. That's got to be temperature. So now it's just a matter of looking and matching our choices to the appropriate numbers. So W has to be a concentration change, so it must be the addition of hydrogen. X has to be something like a catalyst, and when you look at these, you've got heat, addition of neon, addition of hydrogen, decreasing volume. Well, the only one that sounds something that's not going to change the system is addition of neon, so that has to be 2. And Y, since they're all sharp changes, that must be pressure, and that's number 4. And by process of elimination, we're left with number 1.